But you can sit there.
Nice
Yeah,
to
you
see
can.
you. Nice to see you. Thank you very much.
So first you sit up. Yeah, just this distinguished professor from UMD. I guess most of you, if not everyone knows her very well. She was the head of NASA branch and then the EMC director for many years before the war, I believe. She lived at the end of the 1990s to UMD, and so she has been a professor there. She has done a lot of great work, and won a lot of prize. Just a few examples like the WMO prize, that's very and distinguished prestigious prize. She has a lot of good publications, like for the EMC reanalysis has been cited more than 10,000 times. My paper only been cited by 100. Wow. Okay. So I can go on and on for one day, but let her to present. There's a new study. So for our next round of reanalysis, probably we can use some current research result.
Thank you very much. Thank you very much to Vijay for inviting us to come and talk here. I feel like coming home. I was writing a paper and for some reason I felt like I had to thank all the super people that I've been lucky enough to work and I see you and it's it's been my good luck to work at EMC and at the University of Maryland and other places. So I am here with my former student. I don't know where he's sat. He's very back. He's Sechun Chen, and he has done most of the new ideas and implementations, and as you will see, it's almost like magic, the results that he has gotten. So I'm very grateful to him. So I'm going to talk in two parts. The main part is using future observations to improve the analysis and the forecasts and minimize, and the second part is minimize reanalysis jumps when introducing new observing systems. And this is because Vijay said that ENCEP was planning to perform another reanalysis, and I would like to show you these two components that would help a lot for a reanalysis. So let's start with classic data simulation. In classic data simulation, you have an analysis which combines observations and let's say a 6-hour forecast, and that gives the initial conditions of the model, and we then make another 6-hour forecast and go on like that. So this is what's basically classic, but data simulation has improved so much that now we can use it for new applications, and in particular the analysis has the sum of procedures has improved so much that we can use it to improve the observations and to improve the model. And we have done, I'll show a very short example of improving the model for, sorry. This is a poster, and I'm not going to go through it, but that says using analysis increments to estimate and correct systematic model errors, and it was done by Kriti Bhargava and with support by Vijay, and she wrote first a paper showing that the shape of the model biases, and then a second part where she used the estimated model bias to correct the model forecast, and this shows the impact of that, and over 6 hours, 5 days for different variables. This is temperature and moisture, and if it is red, it's an improvement. So it's kind of the proof of the pudding that we can correct for short term the model bias. So sorry, I forget which way to go. So what I'm going to go through is the now most of the talk is about how we improve the observations, and I'll show you that we improve them. So the basic idea is that we use future observations to quality control the current observations. This is something kind of different, unusual, because we are used to only use the current and the past observations, even when we are doing reanalysis where we know the future observations. So there is it's no sin to use future observations if you can use them, if you have them to be available. And so we use the future observations, and in particular 6-hour forecast, 6 hours away, to check whether the observations are beneficial or detrimental. So what we do is to use the observations 6 hours later. So this is at 6 hours, not at 0, and then either use the observations themselves as a measure of truth, or we do an analysis and use this as a truth, and then we check whether each observation either we use the ensemble forecast sensitivity to observations, which we derived for ensemble data assimilation systems, and we find whether each observation improves or the forecasting is beneficial or makes it worse, detrimental. And we then delete the most detrimental observations and repeat the analysis at T0, not after the 6 hours, but at T equal to 0, we repeated the analysis, assimilating only beneficial observations or the least detrimental observations also. So, sorry, so we do this with all the observations, and as I will show, both the analysis and the model forecast improve substantially, and we can also use it in operational systems without cheating. So as you will see, sorry. Okay. This is a beautiful example of a snapshot of all the observations. Yeah.
So, a quick question. So you do that once, right? You make this discrimination between detrimental and beneficial observations, and then redo and then do a new forecast.
Yeah.
And that's it. And then you move on to the next.
And then you do it again at 6 hours later.
Yeah.
Yeah.
Okay. Got it. You don't take the 6-hour forecast you get from the improved.
No.
Yeah. I do it again. Just once.
So, this is an example of Sechun's artistic abilities also, not just computational. It shows all the observations at the 6-hour time or 0-hour time, and they are either blue or red, depending on whether they improve or they are beneficial or detrimental. And there are some observations, for example, that are strongly very large, which means they really reduce the error quite a lot. And then some that are also large but red. But also we see that there are whole bunches of observations that they look horrible. They also in high latitudes. And we discovered like 8 years ago or something when we started this with Jordan, and that I will show you what they are. Well, I'll show you it later, but they are modest winds, and modest winds have been used for many years. I remember Mitch Goldberg looked at that and said, "Oh, those are modest winds," when he saw that we were having that they were detrimental, and they have been used a lot. And when we went to Wisconsin to try to work with the makers of the modest winds, the developers, the first reaction of the director was, many centers are using modest winds. If you don't want to use them, don't use them. But fortunately there were a couple of people that worked with us. But I will show you what we got from that. And so this is first. Before we go to that modest winds question, I would like to show you an overall result. That's finding the detrimental observations and doing proactive quality control, which is eliminating at least some of them, the worst. And we didn't have access to enough computer time. Even the S4 was not enough. So Sechun used a very efficient system designed by Boyan Lien, and it's a GFS system with some lower resolution, and it only uses prep buffer, so it uses no radiances. But otherwise, it's a perfectly reasonable, efficient, but realistic system. And we used as verification something completely separate, like the CFSR reanalysis. So this is what we got as a result. This shows the analysis and the 24-hour forecast, and I'll show you the 10-day forecast, and the impact of very importantly, we did it over a month and cycle. So we we take now a few detrimental observations, throw them away, and then 6 hours later we do it again, so we accumulate the effect of getting rid of detrimental observations, and that allows to have very good results, and I'll show you more here. So the blue means that the results are better than the control without this, and basically there is almost no red. If you look very, very carefully, there is a little bit of red here. But so both the analysis and the 24-hour forecast verified again the CFF reanalysis are improved globally and this happens for every variable. These are different variables. And these forecast improvements remain significant until the errors saturate at about the end of the integration, which is 10 days, so, which is the kind of empirical predictability of a forecast, especially at this resolution. And this is the figure that kind of makes my heart beat faster every time I look at it. It shows the impact of cycling proactive quality control, average over a month, for all the variables in the northern hemisphere, tropics, and southern hemisphere. And it shows three things. One is in red, is the latest correction that we did in the present 6 hours analysis that we are doing. So red is the immediate correction that we are currently doing. And the green is the accumulated from the past. And the blue is the total, which is the red plus the green. And you can see that there is a very strong accumulation from the successive cycling of the PQC, and it happens in all hemispheres, and most of the benefit comes from the accumulated correction. So this means that we don't need to do the latest one, because we already have a lot already here, so we don't need to use the future observations at this time. It's enough to use the one that we did, all the ones that we did 6 hours ago, or 12, and so on. So it's a very powerful result. And so this indicates that PQC is feasible for operation, even if we don't have the time for an immediate correction in an operational tight schedule. So even if we don't have time, which we do, to correct after the final analysis, GIDAS, even if we don't do that, it still we get most of the benefit.
But you have to go back and accumulate at some point.
Sorry?
You have to go back and accumulate at some point, right?
Sorry, you have to talk louder.
Okay. I was just wondering, the green line is the accumulated without going into the future.
The green line is the accumulated without the latest one.
Okay.
And the red is the total.
Okay.
Which includes the latest one.
Right.
The future, the current future.
Okay. I think I understand. Thank you.
Yeah. Thank you. So now I will briefly explain EFSO and how it works, this magic, and how useful it is in monitoring also the quality of the observations at the analysis time. So this is a schematic that shows we are at time t equal to 0, and we have observations at this time, and we have an analysis, and then we make a forecast for 6 hours, and this is a forecast using the observations. But we can also look at the analysis 6 hours ago that gave the first guess, and make a forecast directly from that to time equal to 6. So in general, this forecast should be worse than this because it doesn't benefit from these observations. So basically, all we do is say, is it better or not? If it's not better, it's useless, and if it's worse, it's detrimental. So, and all that is expressed here in this equation that, amazingly, because I'm not a mathematician, I stumbled and derived it all by myself, miraculously. It shows the difference of the error of this minus this, error square, and then on the right hand side it has an equation which includes a vector of the increments, the observational increments. So for each observation we can compute the specific value, and it's quite simple actually, and it represents what we discussed here. So if we get a negative value for EFSO, it means that the observation reduce the forecast error, so they are beneficial, and if it's red, it shows that the observation increased the forecast error, so it's detrimental. And it's very efficient. It costs almost nothing, because all the matrices above are already computed by the ensemble Kalman filter. And furthermore, another discovery that Sechung made, which is amazing, is that we don't need to repeat the reanalysis without the detrimental observations, as I will show a little bit later. So we only need to apply the EFSO corrections, as Ota et al. Did in our second paper.
Quick question.
Sure.
How do you distinguish between a corrupt observation at t equals 6 from a detrimental observation at t equals 0? So when you look at the error, you look at the error at t equals 6.
At t equal to 6, yeah, it could be.
The observation is corrupt.
We are assuming that the observations are at 6 are either perfect or much closer to truth. We assume that.
Okay.
Good point. Okay, so let me show you this other major result that was done also for 2 periods but this is for 2020 for a month, and this is much closer to operations because it has much higher resolution, 254, which was close to operational at that time, and also it has essentially all the observations are used, and we use for a norm an error norm which is moist total energy, which is an advantage that using an ensemble gives you because, for example, the European Center have something similar that they developed with using the adjoint, and the adjoint doesn't work well with the moist part of the processes, so they can only use, at least a few years ago, they could only use the dry. Haven't checked recently. So, so let's look at the results. And this is the figure that makes my heart stop when I see it. Zechun created this, which shows for all the observations that during one month, every 6 hours, the total contribution of each observing system, either positive, either beneficial or detrimental. And if it's negative, it's beneficial, and if positive, it's detrimental. And here is the modest winds are all this. They have lots of episodes of being detrimental. And I will show you some more results from this. And there is a whole bunch. Actually, I was at the meeting and I gave this talk to Bob Atlas, who was being honored, and he said that this Atlas bush is not his observation. So we have a whole bunch, but not even the modest winds on the average are beneficial, but you can see that there are many cases in which they are detrimental, like we saw in that example that I gave by chance. And the most beneficials are railways on GPS and aircraft. And this would be so simple to implement and have it at hand to give guidance to everybody. It's just, I will be honest, I've been wishing that ENCE will implement this here, and it hasn't happened. And to me, I'm happy because in Korea, where we are both advising, they have decided to implement it. So the first ones to implement it will be Koreans. But I wish, I don't know why we are not implementing it, or you are not implementing it here. So sorry for spilling my beans. So this tells you for every observation whether it's beneficial or detrimental. So Zechun decided to help the creators of modest winds and give them their characteristics. So he plotted the innovation for the U and the V winds. There are 3 types of modest winds: cloud trap, water vapor cloudy, and water vapor clear. And he plotted, depending on the direction of the wind, like equatorward, westward, poleward, eastward, and for U and the same for V. He plotted whether it was detrimental or beneficial and this is shocking, I think, because it says very clearly that there is a very strong tendency for the U wind that has a positive observational increment to be detrimental, and even just using a simple quality control that says if it is positive, they don't use the observations, that will help a lot. But so it should be done. And I am also I haven't been following what goes on with the modest winds, but I would think that this information should be enough to help them correct the algorithm that develops this. It should be used okay. So this is powerful because for any observation you find that you can immediately, for example, get for a new instrument, get the quality control that avoids the observations that are mostly detrimental. And it's very easy to do. And one may think that every instrument has that, but that's not true. For example, these are all the EUMETSAT winds, Gauss winds, JMA winds, and although there is a very tiny credits here in EUMETSAT, there are essentially 99% are beneficial, not detrimental. And this shows also how we can keep track of the goodness of the observations. And this is a monthly average of the contribution of the Reawinsons, whether they are beneficial or detrimental, and all of them are beneficial on the average, although maybe not in the month. There may be more subtle differences, but on the average they are all beneficial except for these two stations in India. We have not yet contacted them, but I gave this talk in Japan, and there were 2 or 3 of my colleagues from South America, and they said, wow, we were so happy that all the South American Reawinsons were blue, not red. And now we go to the amazing findings that Zechun has done with satellite. And let's start with hers, the oldest one. And he just plotted the EFSO for each average for each day or 6 hours, and each for each channel. And guess what? There is this obvious case of channel 13 being detrimental, and it has always been detrimental, and it's used in, as I will show you, in other instruments, and it's always detrimental, and it's still used. So he showed that you can even use this with the hyperspectral instruments, IASI, and so here are the channels for IASI, and these dots are the level. This is 1,000 millibards, and this is 0 millibards. So these dots are the level of maximum intensity for the channel, and you can see that IASI has a whole bunch of detrimental observations, and EARS actually has a single detrimental channel, and it happens to be the same channel 13 that Hertz was using. So it's still being used, but and this is the level. In general, the detrimental are at the level of the surface, and this shows the errors. If it's red, it's detrimental. If it's blue, it's helpful. And there is a problem that is mostly on the surface, and like in Australia or in the tropical oceans. And now it's a comparison. This is a comparison doing it in 2012 and 17. And for example, this is Ayasi, and it had 5 channels or 6 channels that were detrimental, and those are still there, but there is a whole bunch of new channels that are very beneficial. But why not use this all the time and correct this? And ears and hers, yeah, this ears has this detrimental channel, which is the same that hers had many years ago. And all of this is done with a browsing tool for EFSO that Tse-Chun Chen created. So you just choose location time instrument and you instantly get the impact of each observation and the impact. And how about Chris? Chris is most impressive with all this huge amount of information here, but it still has, I think this may be channel 13, but it has a whole bunch of detrimental that should not be used, or at least should be corrected. So now I'm going to quickly show the preliminary results that we got with using the Lorenz model, and what kind of made us have confidence in the results. We used Tse-Chun did these experiments with 40 variables, and they are ordered by order of detrimentality in the initial conditions. And you can see that throughout the integration, the ones that were most detrimental continue being most detrimental, and that even if we don't cycle the PQC, we improve the forecast quite a lot. So, so we rejected, for example, the 10% most detrimental, and we got great results. And this is a very important slide, but I won't have time to discuss it too much. But from the beginning, when Daisuke Hota and Ota, Yoichiro Ota, were collaborating with us using for the first time these ideas, we were convinced that once we found that detrimental observations were bad, we had to take them out and compute again the analysis. And the analysis is the most expensive part. So we were feeling it was expensive to redo the analysis. And actually, Yoichiro Ota, in his first experiment that I asked him to make doing proactive quality control, getting rid of the bad observations, he also used the correction that came with proactive quality control, that tells you how, if you take this observation out, how the analysis should change. And we call that we call that method K. So we call H is repeat the analysis without the observation, so that you do everything non-linearly, most correctly. And K is just use the difference that ESO gives you, so it's already computed. So this is the error that we have depending on the percentage rejected, and H, which we thought was necessary, it's here in blue, and K, which is free, and we thought it was not good enough, is in green. And we can see that actually the one that comes for free is much better than the expensive one. So it turns out that just using the same matrix, gain matrix as before, but modified by EFSO, gives you, it works without blowing up even, and it reduces the error even up to 60 or 70% of rejected observations. So, these are concluding remarks. And do you think I have 10 or 15 minutes high for a second talk? Okay. Or shall we have questions now?
This we reserve the room until 1:30, so but we expect to finish by 1.
Okay.
After at 1 o'clock, some people disappear.
Okay. Okay. So I'll get. I don't know if Yan Zhao is here. No, I guess not. This is work that. Yeah. So. I've been talking on how to improve the observations and how to improve the model bias, but I want to talk about reanalysis jumps. You know, when we did the first reanalysis with 25,000 citations, it turned out that I was I forget the name of a very holy group on NWP that at that time I was the representative, and they said you cannot do reanalysis before 1979 when we had started having satellite data, and we still did it because we did experiments that show that even in the southern hemisphere, the monthly anomalies were remarkably well captured. So we still did it, but there was a big jump without satellite data to satellite data. So the jumps in reanalysis when you put a new observing system are the worst problem that reanalysis has. So. I'm going to talk about what to do with the reanalysis jumps. So why do we get reanalysis jumps? Basically because the model is imperfect, and if this is nature, the model is here, and then if we don't put observations, there is a large difference, and when we assimilate observations, the model becomes closer and closer to nature. So the climatological bias between the forecast and nature decreases with the jump when a new observing system was assimilated, was found. And the purpose of Yang Zhou's dissertation, which unfortunately was never published, but it's a very good dissertation, was to find a way to minimize these climate jumps by learning, by correcting the model. And this is an example that shows the change in precipitation in green in MERA and other reanalysis, and it's very clear that the introduction of, for example, SSMI or ATOS produced a jump in the amount of precipitation, global precipitation. So, yeah, so what can we do? The climatological bias between the forecast model and nature decreases with a jump when new observations are assimilated. So this, one solution is what Compo et al. Did. They said we'll only use sea level pressure observations, and that way we have no jumps, and it's very good for that. But this is also, if you guys do reanalysis, and I would love to hear about that and give you advice of an experienced old person. It should be possible to correct this for these jumps, minimize it, and it's not necessary not to use the observations. So Jan tested 3 possible, plausible methods to avoid jumps, and one is called DKM for a paper that we did, and one is called MERRA because it was based on Eugenia Kalnay, who brought the idea that we should learn how much or the characteristics of the jump and then correct it before the instrument. But he had a method that was not so good. And the third one is a very logical one, which is just take the climatology with and without the observation and correct the climatology. And so all 3 methods try to find the average change in the analysis climatology of the new instrument, and then to add it to the analysis before the instrument, so that the corrects its bias in the climatology. And it turned out that the best results were the first ones. And next, MERRA and the simple climatological difference was the worst. Still, they all improve it. And what are these 3 methods? Let me explain first the climatology. The climatology simply takes an analysis after the implementation of the new observing system, and the analysis that doesn't know anything of it. It's old. And MERRA says what was a natural idea. It said, let's do the data simulation with a new instrument and without the new instrument, and take that difference. And what we didn't think about that, but the student realized that this is what we were doing, is take the analysis with a new system and then subtract the analysis with the analysis that uses the old observations, but with the first guess that has the new observations. And it's difficult to explain why that happens, but that's what they are doing. And what she found was basically that the best error, the smallest error, so the bias, she did experiments with a speedy model because we couldn't afford that, and Ravenson's and Ayer's simulated data, and she found that if we debiased, which means we correct the analysis without the instrument, with this method, the error using the best instrument minus the RMS difference with MERRA was like this. So this says this DKM method was much closer to zero than MER. So it very clearly showed that was the best result. So, let's go through a summary. In reanalysis, we know future observation. So if you are doing reanalysis, even if you don't, if you hate this PQC method, proactive quality control method, and don't want to use it operationally, you can use it in reanalysis because we know the future observation, so why not use it? We know how to minimize the jumps if we introduce new observing systems. So one should compare with the 20th century reanalysis that only uses sea level pressure essentially, and compare the results. And I've been asked recently by paleo people whether we could use this use of future data in paleoclimatology. And I think the answer is maybe it should be possible to some extent to improve the paleoclimatology reanalysis. So I am sure that we have not yet done that with Chun Chen, but we are planning to check how much we can improve a reanalysis by using not just 6 hours, but maybe 12 and 24 hours future data to see if that improves the analysis. I would not, since we are getting so much improvement, I'm sure there's a little bit more coming from that. But I'm not sure that the next week or next month or next year will help. So for that we are planning to develop a kind of a paleo reanalysis in a model that has more than one time scale, not just weather, but for example, we have a model, a toy model that looks like it has weather and El Niño time scales. So we are going to check whether we can do that. And I think this is my last slide. Yeah, it was my last slide. Okay, thank you very much.
Any question in the room?
Yeah.
I have a question.
Oh, Junior.
Yeah.
This is the guy that introduced us to the idea of correcting the jumps, and unfortunately we never wrote the thesis.
Yeah, we should finish it, make it realized in the reanalysis. Yeah. I have a question for the first talk.
Sorry? You have to scream.
Yeah, the first talk. The first talk you talk about the detrimental impact of some observation, so you remove it from the analysis in a second circle. But for this detrimental observation, maybe they are not corrupt, they're just not good for the current data analysis or model. The model and data analysis cannot digest the correct information in some time. So is that possible, like use this detrimental observation you don't use to investigate to improve the model and the data analysis?
Yeah. I put I made it look like if all detrimental observations go into a garbage container, and that's wrong. One should use them. And I showed an example where they are used for the modest winds, and you see that when observation of U is larger than the forecast of U, they are wrong. They are detrimental. So that's a news like you are saying, and also it provides an immediate quality control for a new observing system. If you just temporarily not use those observations but study why they are bad, one should use the detrimental observations. But on the other hand, Michael Gill had a discussion, a long discussion when we presented this in Italy, and then here he feels that that every observation should be used, and like you say, to correct it if it is bad, but that if you have random errors, then you should not throw away because it has to then. But I seem to have convinced him that that's when we don't look at the future data. If you know the truth, then we can tell which ones are helping now or not, but we should use the detrimental data and hopefully eliminate them.
Right. I totally agree. What I mean that some data maybe they are not so useful now, but after you improve the data simulation and the model, they can be more useful.
Yeah. Thank you very much for having guided us with
Any question from online? No question.
Because we still work over there.
Eugenia, the biggest jump in all the reanalyses is when you go from the TOVs to the ATOVs time period. Will this
where you go from those
TOVs to the ATOVs in 1998?
Sorry, the last one is what?
ATOVs.
ATOVs, yeah, of course.
From SSU to AMSU and from...
Yeah.
So
the AMSU, when you compute how much beneficial they are, the AMSU top everything.
right, so how do you transfer what you know about the the ATOVs time period and use that in the TOVs time period?
Well, I think basically what we will do is do a reanalysis, let's say with a new instrument, AMSU, including a period where you have an AMSU, and then run it again without AMSU, and we use the change in climatology for that period with and without AMSU and apply it to before.
Okay.
John.
I thought in terms of the first question that we did a little bit of this kind of work in terms of a monitor, and we were deciding that you change the weighting of some of the observations. You don't actually discard them at all, and since it's already a system for weighting all ops, it just fits in. You weight these and they're still there in the following iterations.
Yeah, I agree. It's completely within the spirit of what we are doing. Yeah?
Yeah, hi, just to follow Eugenia Chen's question. So whether the observation is beneficial or detrimental is because whether it can reduce the ESO, ensemble forecast sensitivity observation. So yeah, it kind of on whether it can reduce the forecast error values. So based on the equation, in that slide, so the observation, the value itself is not involved in the calculation of forecast error, right? It's not the value itself. It's whether where the observation is, or the R and the other. But so it seems that it's not the observation, whether the observation is good or bad.
Yeah.
The observation value itself is not involved, right? So you calculate the ESO, right?
Yeah. So the absolute value itself is not.
It's not involved.
It
doesn't matter whether the observation is bad.
So if there's a scenario where all the radii observations are dropping out, what are you going to do?
Sorry, I cannot hear you.
If you have a scenario where some of the radii observations, which are the anchor and the best observations you have, are showing this, and you're going to throw them all out? His thing is like we have to give some weight to how we show these odds are.
Post a copy.
The way of pure.
Do you have will you be posting a copy somewhere?
Yeah, I have that permission.
That would also never
Can you send that out?
because for any individual cycle,
She's going to post a website or you can get it.
it's positive and 45%.
You already post on the website.
Yeah, this is not
Not yet.
Right, that's where I'm just clarifying that the scenario.
Yes, it's posted from the
Yeah.
I just wonder, it's not.
I guess it's getting later. I mean, if anyone want to deal with it.
The value is not based on the value of the.
No. It has to do with how it's projecting onto the 6-hour forecast here.
So the value is important.
I think it's not about
I think
But your observation,
we
your
have
observation
to
that
wrap
it's
up
localized,
the
may relate to the question as to whether it's the model problem or the data problem.
We have room until 1:30.
Okay.
Yeah, well, another seminar there, and anyone want to
This is the time to escape.
Yeah, well, people start leaving for other meetings.
So it could be detrimental either because the value wasn't good,
Yeah, why
or because the model.
why don't we continue the discussion
After the seminar.
including that?
Yeah.
Okay.
Okay, thank you.
Okay.
Let people go out.